Hello everyone, this is Ma'am Amano, and this lecture video is all about the parts of a chemical equation, types of chemical reactions, and chemical balancing. Let us define first the chemical equations. These are representations of chemical reaction in terms of symbols of elements and formulas of compounds involved in the reaction. As such, the parts of a chemical equations are as follows. We have here the forward arrow. This forward arrow separates the reactants from the products. So the reactants here are written on the left side of the arrow, while the products here are written on the right side of the arrow. It is read as yields, produces, or forms. For example, 2 moles of hydrogen gas plus an oxygen gas will yield 2 moles of water, or 2 pieces of water, such as that. So this one is read as yield, produces, or forms, since that is a forward arrow. Then we also have here the plus signs, which separates the formulas of the reactants or products if there are more than one reactants or products. Then we also sometimes uses the delta sign, which indicates a heat, especially in the decomposition reaction. So this delta sign here signifies that the reactant is heated. And we also have here the coefficients. So this coefficient is a number that appears before the symbol or formula. This indicates the number of moles of the substance involved in the reaction or the number of compounds present. So for example, here we have 2 pieces of water indicated by the coefficient, 2 pieces of hydrogen gas. So if no coefficient appears before a given formula, then it is understood to be 1. And then we also have here the subscript. You don't have to change the subscript, you just have to put a coefficient here. Because if you change the subscript of the compound, then it is no longer the same product that you are balancing or in the reaction. So we must abide in the law of multiple proportions, in which you just have to put a coefficient here and not to alter the identity of the compound that you are balancing. Now let us proceed on types of chemical reactions. On this lecture video, we will be tackling the following chemical reactions. These are the combustion reaction, addition or composition reaction, single replacement reaction, double replacement reaction, and decomposition reaction. Before we proceed, let us define first a chemical reaction. It transforms one or more substances. The substances that enter into a chemical reaction are called the reactants, and the substances formed are called the products. First type of reaction, we have here the combustion reaction. This is a reaction of an element or compound with oxygen to form an oxide and produce heat. So the reactants for combustion is a hydrocarbon, and then that will react into an oxygen gas to produce water and carbon dioxide gas. So the X and Y here represents the subscripts present in a hydrocarbon. So for example, we have here a methane, and that will react on the oxygen gas, and therefore it will produce a water and carbon dioxide gas. Another example, we have here pentane. It will react on oxygen gas, and it will produce water and carbon dioxide. Now, in chemical reactions, especially in the chemical equations of those reactions, it is a requirement that the equation has to be consistent with the fundamental law of nature, which is the law of conservation of mass. Meaning to say, we have to balance these equations here. Meaning to say, when it undergo a reaction, the mass of the reactants must be equal to the mass of the products. So, for example, on the combustion reaction, we have here the reaction of methane and oxygen gas, which will yield water and carbon dioxide. For the initial number of elements in each compound in reactants and products, we have here the carbon, hydrogen, and oxygen. Initially, the carbon on the reactant side, on this part, this is your reactant side, and this is your product side. Let us tackle this one by one. So, in the reactant side for carbon, we have 1 piece of carbon. Since it doesn't have a subscript, then that means that it is 1 piece of carbon. And then we have here 4 hydrogen by the presence of the subscript. And then we also have here 2 pieces of oxygen. On the product side, we have here the 1 piece of carbon, then 2 pieces of hydrogen, and then 3 pieces of oxygen. That is 2 here, plus 1 here, that is 3. So as you can see, they are not balanced. The only balanced element on the reaction is the carbon, but the rest, it is not balanced. It is not balanced because they do not have the same number of the element in the reactants and product side. So we have to balance them by adding a coefficient. So on this case, to analyze that, we have here hydrogen, 2 pieces, and then 4 hydrogen here. So we will add 2 here by analyzing. You will have to start on the smallest number in the trial and error. It is always a trial and error. And you should start always in the simplest and smallest number possible. Of course, you wouldn't use 1 because it will yield the same number. So you will start with 2. If it is not balanced in 2, then you should try the 3 and so on. And by inspection, we can tell that we have to add 2 here. Let me use a blue color here on this side, the coefficient. So let us count again the number of the elements in each reactants and products. For carbon, we still have the number 1 carbon here, balanced. For hydrogen, we have here now on the reactant side that is 4 and the product side that is 2 times the subscript of the hydrogen that is 4. So we have here 4 hydrogen and that is therefore balanced already. So on the reactant side that is 2 here, and then on the product side that is 2 times 1 here that is 2 plus 2 here that is 4. And as you can see, it is not balanced. To balance this, furthermore, we have to add 2 here on the oxygen gas on the reactant side. And then, so that will be 2 times 2 that we have here now for oxygen. So as you can see, we already have the same values for the carbon, hydrogen, and oxygen, both on the reactant and product side. Therefore, this is now a balanced equation. Another example of the combustion reaction and the balancing as well, we have here the reaction of pentane to the oxygen gas, which will yield water and carbon dioxide gas. So by inspection, we have to analyze the initial values of each element in the reactant and product side. This is your reactant here, this is your product side here. For carbon, we have here 5 pieces of that, determined by the subscript. For hydrogen, we have 12 pieces of that. And then for oxygen, we have 2 pieces of that on the reactant side. On the product side, for carbon, we have 1 piece of that. For hydrogen, we have 2 pieces of that. For oxygen, we have 3 pieces of that. This is 2 plus 1 oxygen here, that is 3. So as you can see, this is not a balanced equation and we have to balance this one. So you have to put here 8, and then 6 here, and then 5 here. You will do a trial and error until you achieve these numbers. Okay, so for carbon now, we have how many pieces? We still have 5 on the reactant side. And then on the product side, we have 5 carbons here. 5 multiplied to the subscript of carbon, which is 1. That's 5 times 1. So you now have here 5 pieces of carbon on the product side. Now for the hydrogen, we have here 12 pieces of that originally. And then on the product side, you have here your 6 as coefficient multiplied to the subscript of the hydrogen, that is 12. So the new number of hydrogen is 12 already. And then for oxygen, you have here 8 times 2, that is 16. So this will be 16. And then on the product side, that is 6 times 1 here, that is 6. And then 5 times 2, that is 10. 10 plus 6, that is 16. So it is already a balanced equation. Okay? Another example is the reaction of methanol. This is CH3OH as well, CH3OH, or can be expressed as CH4O for methanol. Now for methanol that will be reacting on oxygen gas, since that is a hydrocarbon, it will produce or will yield water and carbon dioxide gas. By inspection and by counting, we will know the initial value of the elements. For the reactant side, we have how many pieces of carbon? We have 1 of that here. For hydrogen, we have 4 of that here. And then for oxygen, we have 3 of that. 2 plus 1, that is 3 here. Now on the reactant side, we will have here how many pieces of carbon? We have 1. For hydrogen, we have 2. For oxygen, we have 3. 2 plus 1 here, that is 3. So as you can see, the equation is not balanced on the hydrogen side. So by inspection, we have to put 2 here on the coefficient side of the methanol, and 3 here on the oxygen gas, and then 4 here on the water, and then 2 here on the carbon dioxide gas. You will arrive on those numbers by trial and error. So let us count the final values of the balanced reaction. For carbon, how many pieces of carbon do we have already? On the reactant side, we have here 2 pieces of that. 2 times the subscript of carbon, which is 1, that is 2. And then for hydrogen, we have how many pieces of that? On the reactant side, that is 4 times 2 here, that is 8. And then for oxygen, how many pieces of that? You have here 2 times 1, that is 2. Plus 3 times 2, that is 6. 6 plus 2, that is 8 oxygen here. And then on the product side, we have here how many pieces of carbon? That is 2 times 1, that is 2. You have now here 2 for the carbon. And then for hydrogen, that is 4 times 2, that is 8. And then for oxygen, that is 4 times 1, that is 4. Plus 2 times 2, that is 4. And 4 plus 4, that is 8 oxygen here. By inspecting, that is already balanced. So let's check. So let us proceed on another type of chemical reaction. We have here the addition or composition reaction, in which we can define it as one in which 2 substances react to form 1 compound. This is also known as combination, direct union, or synthesis reaction. The general form of this reaction is A plus B, and that will yield an AB, wherein the A and B can be an element or a compound. For example, I have here the reaction of sodium into the chlorine gas, and it will yield a sodium chloride. Why? Again, on writing the products in terms of ions here, you will disregard the subscript. So the sodium, we have here positive 1 as its reactants, and then the chlorine disregarding the subscript, that is -1. So interchange, you will have the NaCl. But by inspection, you can tell that this is not a balanced equation. From the reactant side, we have here the 1 piece of sodium. And then for chlorine, we have 2 pieces of chlorine. On the product side, we have here the 1 piece of sodium and 1 piece of chlorine. So therefore, this is not a balanced equation. To balance this one, you will need to put, you have to balance the chlorine, right? And we have 2 here, so I have to put 2 here as its smallest coefficient possible. So, and then, since you added 2 coefficient here, that will also increase the number of sodium. So you have to add 2 here on the sodium side. So that will be how many right now? For the reactant side, we have 2 pieces of sodium. And chlorine is still 2 pieces. On the product side, we have 2 pieces of sodium already, 2 times the subscript of sodium, which is 1, that is 2. And then for chlorine, 2 times the subscript of chlorine, that is 2. So therefore, this is now a balanced equation. Another example is the reaction of barium plus oxygen gas. The barium has a 2 plus charge, and the oxygen have a -2 charge. So interchange, that will be Ba2O2, and cancel the 2 here in the empirical formula. It must be in simplest form, which is BaO, or barium oxide. And then by inspection, you can tell that they are not equal. For the reactant side, we have 1 barium. For oxygen, we have 2 pieces of that. For barium, we have 1 pieces here in the product. And then for oxygen, we have 1 piece of that in the product. So to balance this equation, you will put here 2 here, since you have 2 pieces of oxygen on the reactant. So you have to balance the product side by putting 2, of course. Not 3, not 4, because you have to start with the simplest. And then for barium, you will increase the barium on the product side. So you have to put 2 here. Okay, so let us check if they are already balanced. In the reactant side, we have now 2 pieces of barium. For oxygen, 2 pieces of oxygen. And then on the product side, we have already 2 pieces of barium. And 2 times 1 for oxygen, that is 2 pieces of oxygen. So therefore, this equation is already balanced. Another example, I have here the reaction of magnesium and sulfate. So the reaction will yield magnesium sulfate. So why? Because the magnesium here, we have 2 plus, the charge of that. And sulfate has a 2 plus charge. 2 negative charge. So interchange, that will be Mg2SO42. So cancel the charges, you will have this product here. Let us analyze if they are balanced already. So we have here for magnesium 1 piece of that. For sulfur, we have 1 piece of that. For oxygen, 4 pieces of that. On the product side, we have magnesium 1 piece of that. For sulfur, 1 piece of that. And for oxygen, 4 pieces of that. So you do not have to balance this equation or reaction since they are already balanced. Now let us proceed on another type of reaction, which is the single replacement reaction. So we can define this reaction as one in which a cation replaces another cation, or an anion replaces another anion. This is also known as displacement reaction or substitution reaction, in which the general form is AX plus B, which will yield BX plus A. Okay, as you can see, it replaced the cation here, the A, and it will yield now BX plus the free metal here. And then you will have here AX plus Y, in which it will replace the anion here. Okay, because the A and B are metals, these are metals, and the X and Y are non-metals or anion, and the A and B are cation. So let us proceed. For example, I have here the reaction of copper sulfate plus the iron. So as you can see, the reacting element is a cation. This one is a positive charge. So this one is a metal or cation. Therefore, it will replace the copper here. So meaning to say, the iron will react on the anion sulfate. The charge of iron is 2 plus. And the charge of sulfate is -2. SO4, -2. So interchange of charges, you will have FeSO4 as your product. And then the copper here will be a free metal, and that will be copper, just standalone copper. So let us check if they are already balanced. For copper on the reactant side, we have 1 piece of that. For sulfur, we have 1 piece of that. For oxygen, we have 4 pieces of that. And then for iron, we have 1 piece of that. On the product side, we have here 1 piece of copper, 1 piece of sulfur, 4 pieces of oxygen, and 1 piece of iron. So you don't need to balance this equation since this is already balanced by the same number of elements. Another example, I have here the reaction of sodium hydroxide with the potassium. So this is an example of an cation replacing the cation here. So meaning to say, the potassium here will react on the anion group hydroxide. The charge of potassium is +1, and the charge of hydroxide is -1. So they will interchange. You have here OH, So this one will be the subscript of OH and this one will be the subscript of potassium, and that will become positive. So you have now the potassium hydroxide here. And then the sodium that has been replaced will become a free metal, just a standalone sodium metal here. So let us analyze if they are already balanced. For the reactant side, we have one piece of sodium. For oxygen, we have one piece of that. For hydrogen, we have one piece of that. And for potassium, we have one piece of that. On the product side, we have one piece of sodium, one piece of oxygen, one piece of hydrogen, and one piece of potassium. So we therefore no longer need to balance this equation or reaction since this is already balanced by the presence of the same values in each elements both in reactants and products. Now, under the single replacement reaction, let us have an example in which an anion will replace another anion. So, we can tell that that is an anion by the presence of the metal which has a charge of the negative. So, in this case, we have here the sodium iodide plus the chlorine gas. So, a chlorine gas is an anion and it will replace the anion here. So, meaning to say the sodium will react on the chlorine and the sodium has a charge of positive 1 and the chlorine has a charge of negative 1. You will disregard again the subscript. You will focus on the charge of the element. So, they will interchange for sodium. This one will be the subscript of this one will be the subscript of this one, and will become positive. And therefore, you will have the sodium chloride here. So, when an anion replaces another anion, the anion that has been replaced will become a gas. Okay, unlike the other example, which is just a free metal. So, in this case, it will become a gas, and therefore, we'll have a subscript of 2. On this case, we have here the iodine gas. Okay, so let us check if they are already balanced. I have here sodium. On the reactant side, 1. On the iodine, we have 1 piece of that. For chlorine, we have 2 pieces of that. On the product side, we have here the sodium, 1 piece of that. For iodine, we have 2 pieces of that. And then for chlorine, we have 1 piece of that. So, as you can see, this is not a balanced equation. To balance this reaction, we can add 2 here on the NaCl. So, let us check if they are already balanced. On the product side, we have now here 2 pieces of sodium. And then, for iodine, 2 pieces of that. For chlorine, 2 pieces of that. So, as you can see, it is not yet balanced. So, I guess we have to add 2 here. So, you will now have on the reactant side 2 pieces of sodium. And then, 2 pieces of iodine. So, as you can see, this is now a balanced equation. Okay? And then another example for an ion replacing another anion under the single replacement reaction, I have here the dilithium oxide plus the chlorine. So, meaning to say the lithium here will react on the chlorine. So, the charge of lithium is positive 1 and the charge of chlorine is negative 1. So, interchange of charges, you will have the lithium chloride here. Since the replacing element is a type of an ion, therefore the replaced anion will become a gas, which is the oxygen gas. Let us check if they are already balanced. For lithium, on the reactant side, we have 2 pieces of that. For oxygen, 1 piece of that. And then for chlorine, 1 piece of that. On the product side, we have 1 piece of lithium. And then for chlorine, we have 1 piece of that. And for oxygen, 2 pieces of that. So as you can see, this is not a balanced equation. So we have to balance this by putting here, let us say, we have to put 2 here. Okay. And then 2 here, since you will add that. Okay, so let us check if they are already balanced. On the reactant side, we have 2 pieces of lithium as still. For oxygen, we have 1 piece of that. So I guess you need to add 2 pieces of oxygen here. So let us check again. So that will be 4 already. And then for oxygen, you have now 2. And then for chlorine, you have now 2. And then on the side, you have, so you have to change this one into 4. For lithium here, so that will be 4. And then for oxygen, that is still 2. And then for chlorine, that is 4 pieces of chlorine. So this chlorine here is not yet balanced, so you have to change this 2 here into 4. So you now have 4 here. So they are already balanced. Another type of reaction is a double replacement reaction, in which 2 compounds react to form 2 new compounds. This is also known as exchange reaction or metathesis. So the general form of the equation of this one is AX plus BY, in which the anions will be swapped with their cations and therefore will produce AY plus BX. Let us have an example of this reaction. I have here disodium sulfate, which will react on barium chloride. So there will be an exchange of anions. Okay, so the sodium here will react on the chlorine and the barium here will react on the sulfate. So let us react the sodium, disregard the subscript, to the chlorine. So this is positive 1 and this is negative 1. So you will have sodium chloride on this reaction. And then for the reaction of barium and the sulfate here, barium is 2 plus, sulfate is negative 2. Negative 2, that is negative 2. So cancel, you will have this reaction, BaSO4. Let us analyze if they are already balanced. We have here, for sodium, we have 2 pieces of that. For sulfur, we have 1 piece of that. For oxygen, we have here 4 pieces of that. And for barium, we have 1 piece of that. For chlorine, we have 2 pieces of that based on the subscript here. Now, on the product side, we have 1 piece of sodium, 1 piece of sulfur, 4 pieces of oxygen here, and then 1 piece of barium, and then 1 piece of chlorine here. So, as you can see, this is not a balanced equation. To balance this one, we have to add, I guess, we have to add 2 here on the sodium chloride product side. So, let us check again. We have here now 2 pieces of sodium and then 2 pieces of chlorine. That is 2 times 1 here. So that is 2. So as you can see, they all have the same values already. So therefore, this equation is already balanced. So another example, I have here the reaction of potassium chloride and beryllium dichlorate. So this is beryllium dichlorate. So in this case, the potassium will react on the chlorate here. And then the beryllium will react on the chloride here. They will interchange. Okay? So, let us react potassium and the chlorate. Okay? So, the charge of potassium is positive 1. And the charge of chlorate is negative 1. So, cancel, you will have here the potassium chlorate. And then, let us react the reaction of beryllium, which is Be. And then, the chloride here, which is ClO2. The charge of beryllium is 2 plus. The charge of chloride is negative 1. So they will interchange. The beryllium here, this one, will have a subscript of this one. And then the chlorate, Cl2, will have the subscript of 2 plus here. This one. Okay? And that is how it produced the product. So let us check if this is already a balanced equation. We have here on the reactant side, 1 piece of potassium. For chlorine, so if there's a parenthesis, you have to distribute the subscript outside of the parenthesis in the inside element. So in this case, we have 1 piece of chlorine on the inside and then a subscript 2 here outside the parenthesis. So that is 2 times 1 here. 2 plus 1 here, we have 3 chlorine. And then for oxygen, we have 2. And then 3 times 2, that is 6. 6 plus 2, that is 8 oxygen here. For beryllium, we have 1 piece of that. On the product side, we have here 1 piece of potassium. For chlorine, we have, let us say we have 1 and then 2 times 1. 2 plus 1, that is 3 here. For oxygen, we have 2 times 2, that is 4. And then plus the oxygen here, which is 3, that is 7. And then for beryllium, we have 1 piece of that. To balance this equation, I guess we need to put 2 here. So on the product side, we have now 2 pieces of potassium. We have now how many pieces of chlorine? We have already 2 times 1 here, that is 2. Plus 2 times 1, that is 2, that is 4. We have 4 chlorine here already. And then, how many oxygen do we have now? That is, on this one, that is 4. And then, 3 times 2, that is 10. So, you now have 10 oxygen here. And then, for beryllium, we still have 1 beryllium. And then, I guess we have to add 2 here on the reactant side to balance the other values. So, how many potassium do we have now? 2. And then, how many chlorine? We have here 2 times 1, that is 2. Plus, here, 4. This one, 2 times 1 here, that is 4. And then for oxygen, we now have 2 times 2, that is 4. Plus 3 times 2 here, that is 6. So that will be 6 plus 4 here, that is 10. And then beryllium is always 1. So we already have a balanced equation here. Another type of reaction is the decomposition reaction, in which this is a reaction in which a compound decomposes to form 2 or more new substances. So usually heat is necessary to cause this reaction to take place, and this is also known as analysis reaction. The general form of this equation is AB. When heated, it will yield A plus B. So this is a separation reaction, okay? So under decomposition reaction, we will be tackling the following decomposition of compounds: the hydrates, chlorides, metal oxides, carbonates, hydrogen carbonates except 1A metals, and hydrogen carbonates of the group 1A metals. So let us start with the decomposition of hydrates. So when heated, it will decompose to yield water and the anhydrous salt. So this is the hydrates here. As you can see, there is a compound wherein a water molecule is attached on that. So when this compound is heated, denoted by the delta sign here, it will be separated. Okay, so you will have here the barium chloride plus the 2 pieces of water. So let us check if this is already a balanced equation. For barium, how many pieces of that? We have 1 piece of that. And then for chlorine, we have 2 pieces of that. For hydrogen, we have 4 pieces of that. 2 times 2, that is 4. And then for oxygen, 2 times 1, that is 2 pieces of that. On the product side, we have here 1 piece of barium, 2 pieces of chlorine. For hydrogen, that is 2 times, so that is 4. And then for oxygen, that is 2 times 1, that is 2. So as you can see, we already have a balanced equation because we just split the barium chloride and the hydrate here. So it will have the same amount. Okay, and therefore this is a balanced equation already. Another example for the decomposition of hydrates, in which when heated, it will produce a sodium chloride. It will be depleted here, and 7 molecules of hydrates or water here. So as you can see, the reactant and product side has the same number of elements. So therefore, this equation is already balanced. Now let us proceed on the decomposition of chlorates. So when we talk about chlorates, these are compounds having chlorates, ClO3, on the cation. So this is the anion group that attaches on the cation. So when heated, these chlorates will yield or decompose chloride plus oxygen gas. So for example, I have here the reaction of potassium chlorate. How did we obtain this product? We have here the charge of potassium is positive 1, and then the chlorate is, we have here the negative 1, since that is an anion. And then cancel, you will have this product here. Every chlorate that decomposes or heated will yield a chloride and an oxygen gas. So when we talk about chlorates, these are compounds having chlorates as their anion, and then it will yield a chloride or a metal ion with chlorine as its anion, and then an oxygen gas. So meaning to say, we have to react potassium and chlorine, or the cation to the chlorine. Reacting that, this is a positive 1 and this one is negative 1. Negative. For that, cancel, you will have this chemical formula here. Plus oxygen gas. This is the format or the rule. Okay, based on the study. So we have here how many pieces of potassium on the reactant side. We have 1 of that. For chlorine, 1 of that. For oxygen, 3 of that. For potassium on the product side, we have 1 piece of that. For chlorine, 1 piece of that. And for oxygen, 2 pieces of that. So as you can see, this is not a balanced equation. To balance this one, we have to put 3 here, and then 2 here, and then 2 here. We have here now 2 pieces of potassium. For chlorine, we have 2 pieces of that already. 2 times 1, that is 2. For oxygen, we have 2 times 3, that is 6. On the product side, we have 2 pieces of potassium, 2 pieces of chlorine, and then 3 times 2, that is 6 pieces of oxygen. So therefore, this equation is already balanced. Another example for chlorates decomposition, we have here the barium dichlorate. Okay, how did we arrive this reaction? We have here the charge of barium is 2 plus, and the charge of chlorate is negative 1. So we have here the Ba, and this one will be the subscript of barium here. And then since this one is more than 1, you will have to put an open parenthesis and then subscript of 2. So that is why how we obtain this chemical formula. And then every chlorate again that will decompose, meaning to say every cation having chlorate as their anion group will yield a chloride, meaning to say a chlorine that is attached on the cation, and oxygen gas. That is the rule. So meaning to say we have to react the barium on the chlorine. The charge of barium is 2 plus, the charge of chlorine is negative 1. So we have here now the Ba is 1, and then the chlorine is 2. So therefore, you have this chemical formula here. Now let us check if this is already a balanced equation. For barium, we have on the reactant side, we have 1 piece of that. For chlorine, we have 2 pieces of that, 2 times 1 here, that is 2. For oxygen, we have 6 pieces of that. Now on the product side, we have 1 piece of barium, 2 pieces of chlorine here, and then 2 pieces of oxygen. So as you can see, this is not a balanced equation. To balance this one, we have to balance the oxygen here. So we just need to put 3 here to balance this one. So that is 3 times 2, that is 6. So this one, therefore, is already a balanced equation. Another reaction for decomposition is the decomposition of metal oxides, meaning to say the anion of the compound is oxygen. Okay, so when heated, it will decompose to form the free metal and oxygen gas. For example, this one is an oxide because the anion is an oxygen. So this one is mercury oxide. When heated, it will produce the free metal, the cation, the free cation, plus the oxygen here will become an oxygen gas because it has been heated, evaporated. And then let us check if this is a balanced equation. We have here on the reactant side 1 piece of mercury, and then for oxygen 1 piece of that. On the product side, we have 1 piece of mercury and then 2 pieces of oxygen. So as you can see, this is not a balanced equation. To balance this one, I guess we need to put 2 here as the coefficient, and then 2 here as well. Okay, because we need to balance the oxygen, so we will be putting 2 here for the oxygen here. So let us check if this is already a balanced equation. How many pieces of mercury? We have 2 pieces of mercury. And then how many oxygen? 2 pieces of oxygen. On the product side, we have 2 pieces of mercury and then 2 pieces of oxygen. So therefore, this equation is already balanced. Another example for the decomposition of metal oxide is calcium oxide. How did we obtain this? Again, the charge of calcium is 2 plus, the charge of oxygen is negative 2. Cancel, you will have calcium oxide. And when heated, it will produce the free metal, which is the cation, and then an oxygen gas. That is the rule. So let us check if this is already a balanced equation. We have here 1 piece of calcium, 1 piece of oxygen. On the side product here, we have 1 piece of calcium and then 2 pieces of oxygen. So as you can see, this is not a balanced equation. To balance this one, I guess we have to add here 2 on the coefficient here and then 2 here as well. So let us check 2 pieces of calcium and then 2 pieces of oxygen. On the product side, we have now 2 pieces of calcium and then based on that and then 2 pieces of oxygen here. So therefore, this equation is already balanced. Another type of decomposition is the decomposition of carbonates. Carbonates is CO3. This is an anion group, and the charge of that is negative 2. So when heated, those compounds having carbonates as their anion will decompose to form oxides and carbon dioxide gas. For example of carbonates, we have here calcium carbonate. So as you can see, the carbonate is the anion group in this compound. How did we obtain this one? The calcium is 2 plus. The charge of carbonate is negative 2. So cancel, you will have calcium carbonate. And when heated, it will produce again an oxide, meaning to say you will have to react the calcium on the oxygen. The calcium is 2 plus, the oxygen is negative 2. So cancel, you will have this one. And then it will produce as well a carbon dioxide gas. That is the rule. Let us analyze if this is already a balanced equation. For the reactant, we have 1 piece of calcium. For carbon, we have 1 piece of that. For oxygen, 3 pieces of that. On the product side, we have 1 piece of calcium, 1 piece of carbon, and then 3 pieces of oxygen because you have here 2 plus 1, that is 3. And therefore, we do not need to balance this one because this is already a balanced equation. Check. Another example for the carbonates is the decomposition of zinc carbonate. So when heated, it will produce an oxide and then carbon dioxide gas. So this one is a carbonate because we have here the anion group of carbonate. So the charge of zinc is 2 plus. The charge of carbonate is negative 2. So that is cancel, you will have this value here as zinc carbonate. And then when heated, it will produce an oxide. Meaning to say it will have an oxygen as an anion. So therefore, the metal here, the cation here, we need to react that into the oxygen. So again, zinc is 2 plus, oxygen is negative 2. So cancel, you will have this one. And then automatically, the carbon dioxide gas will be produced. Let us check if this is a balanced equation. We have here 1 piece of zinc, 1 piece of carbon, 3 pieces of oxygen, and then 1 piece of zinc on the product side, 1 piece of carbon, and then 3 pieces of oxygen. That is 2 plus 1, that is 3. So we do not need to balance this one because this is already a balanced equation. Another example is the decomposition of hydrogen. Carbonates except 1A metals. For hydrogen carbonates, which is also known as bicarbonates, the chemical formula of this anion group is HCO3 and the charge is negative 1. When heated, it will decompose to form oxide, water, and carbon dioxide gas. So, for example, for you not to be confused, this reaction will disregard the 1A metals, which are the hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. So these are the 1A metals and we have to disregard that on the reaction, meaning to say it will have a different decomposition reaction. So for this equation, we have here the decomposition of calcium dihydrogen carbonate. Okay, so we have, how did we obtain this equation? We have calcium as 2 plus. And then the bicarbonate is negative 1, the charge of that. So interchange, you have here Ca, and then this one will be the subscript of calcium here, and then HCO3, and then this one will be the subscript of 2 here. So that is how we obtain this value here. So when heated, the calcium dihydrogen bicarbonate, when heated, will yield an oxide, meaning to say we have to react the metal on the oxygen, that is calcium reacting to the oxygen. 2 plus, that is cancel, you will have here the calcium oxide, and then it will produce as well automatically a carbon dioxide gas and then the water. So let us check if this is a balanced equation. For calcium, we have here 1 piece of calcium on the reactant side, 2 pieces of hydrogen, that is 2 times 1 here, 2, and then the carbon is 2 times 1, that is 2, and then for oxygen, that is 6, 2 times 3, that is 6. In the reactant side, we have 1 piece of calcium, 2 pieces of hydrogen, 1 piece of carbon here, and then 4 pieces of oxygen. That is 2, 3, 4 pieces of that. So as you can see, this is not a balanced equation. To balance this one, I guess we need to put 2 here. So let us check. How many carbons do we already have now? We have 2 pieces of that. That is 2 times 1 here. And then how many oxygen is 2 times 2? That is 4, 5, and then 6. So we have now 6 oxygens. So therefore, this is already a balanced reaction. Another example for the decomposition of hydrogen carbonates with the exemption of 1A metals. We have here barium, which is a 2A metal. And then that is barium dihydrogen carbonate. So how did we obtain this one? The charge of barium is 2 plus, and the charge of hydrogen carbonate is negative 1. So they will have just to interchange their charges as subscript. So you will have barium here, and this one will be the subscript of the here, and then HCO3, and then this one will be here too. So that is how we obtain this formula. And then when heated, every hydrogen bicarbonates with the exemptions of 1A metals will yield an oxide, a carbon dioxide gas, and then of water. So meaning to say we have to react the barium or the cation into the oxygen. The charge of barium is 2 plus. The charge of oxygen is negative 2. Cancel, you will have this formula, and then automatically carbon dioxide gas and then water. So let us check if this is a balanced equation. How many barium do we have? On the reactant side, we have 1. How many hydrogen? We have 2. How many carbon? We have 1 times 2, that is 2. How many oxygen? That is 6. 3 times 2 here. On the product side, we have 1 barium, and then hydrogen is 2, and then carbon is 1, and then oxygen is 4, that is 2, 3, 4. So to balance this one, since this is not a balanced equation, we have to add 2 here on the carbon dioxide gas. So let us check again. We have now how many pieces of carbon? 2. 2 times 1, that is 2. And then how many pieces of oxygen? We have 2 times 2, that is 4, 5, and then 6. So we have here 6. So this is therefore a balanced reaction already. Another type of reaction for decomposition is the decomposition of hydrogen carbonates of the 1A metals. So when a cation from 1A metals has been attached on an ion group of hydrogen carbonate, okay, the charge of hydrogen carbonates is HCO3, and that is negative 1. So the 1A metals that will react on the hydrogen carbonates, these are the 1A metals, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. It will produce a carbonate, a water, and carbon dioxide gas. So when we talk about carbonate, these are cations that has cations attached on a carbonate, CO3, as it's an ion. So let us have an example. I have here sodium, which is a 1A metal, and that is sodium hydrogen carbonate or sodium bicarbonate. So when heated, it will produce a carbonate, which is CO3, meaning to say we have to react the sodium into the carbonate. The charge of carbonate, CO3, is negative 2. The charge of sodium is 1. So we have here now the sodium. This one will be the subscript of here. And then the carbonate, this one will be the subscript of the carbonate, CO3. So that is how you obtain this one. So you have here disodium carbonate plus automatically carbon dioxide gas and then water. So let us check if this is a balanced equation. How many sodium? We have 1. How many hydrogen? We have 1. How many carbon? We have 1. How many oxygen? We have 3. For the product side, we have 2 pieces of sodium, and then hydrogen is 2 pieces as well. Carbon, we have 2 pieces of that, 1, and then 2. For oxygen, we have 6 pieces of that, 3, 4, 5, and then 6. Now, this is not a balanced equation, so we have to balance that. To balance that, we need to add 2 here, I guess. So let us check. How many sodium? We have 2. How many hydrogen? We have 2 times 1, that is 2. And then how many carbon? We have 2 pieces of carbon already, 2 times 1 here, that is 2. And then how many oxygen? That is 2 times 3, that is 6. So therefore, this is now a balanced equation. So another example for the decomposition of hydrogen carbonates of the group 1A metals is the decomposition of lithium bicarbonate. How did we obtain this formula? We have lithium and then HCO3. So this one is 1 plus and this one is negative 1. So cancel, you will have lithium bicarbonate here. So whenever a 1A hydrogen carbonate will be decomposed, it will produce a carbonate, meaning to say the cation will react on the carbonate and it will produce automatically the carbon dioxide gas and water. So let us react the lithium on the carbonate, CO3. The charge of lithium is positive 1. The charge of carbonate is negative 2. Okay, that is negative 2 here. So interchange lithium and then this one subscript of that and then CO3. Okay, this one here, you do not need to write the parentheses since it is only 1. So that is how you obtain the product of carbonate here. Okay, and then It will also produce a carbon dioxide gas and water automatically. Let us check if this is a balanced equation. We have here for lithium, 1 piece of that. Here, for hydrogen, 1 piece of that. For carbon, 1 piece of that. For oxygen, 3 pieces of that. For lithium, on the product side, we have 2 pieces of that. For hydrogen, we have 2 pieces of that. For carbon, we have 2 pieces of that. 1, 2. For oxygen, we have 6 pieces of that. 2, 5, and then 6. So, therefore, this is not a balanced equation. I guess we need to put 2 here to balance this one. So, to balance this one, let us check again. How many pieces of lithium? For the reactant side, we have 2 pieces. For hydrogen, that is 2 pieces as well. For carbon, that is 2 pieces as well. And then for oxygen, that is 2 times 3, that is 6. So therefore, this is now a balanced equation. So that is all for this lecture video.